So if you go to open your web browser and watch, some totally random YouTube video, you might notice the little lock in the corner that tells you that everything is secure and no one else can see what you're watching, unless, of course, you broadcast it on YouTube. So how does it actually do that? Well, helpfully, you can click on more information and wait a little bit, and you can see over here it says something about AES and something about GCM. And 128 is just the key size, TLS is the protocol, the actual core cryptography that keeps your stuff. Why did I bang the thing like that? That's not, what am I doing? So there's two sides to this, AES and GCM. I'm going to focus mostly on GCM because I think it's cooler, and also AES is kind of a mess, GCM is a lot easier to understand. But some of this applies to both, and AES part 2 maybe, but we'll actually start with AES, and the fact that AES is a block cipher. And what a block cipher means is that it encrypts multiple bits at a time. So, you have your sequence of bits that you want to encrypt, and we're going to take that big chunk of bits and somehow, encrypt it using a secret key. The trick here is that, this is a fixed size, let's say 128 bits. So you can encrypt a single block of 128 bits, and that's it. No more, no less. To understand how AES does this, we have to talk about a math thing, which is actually really fun, which is called Galois fields. So you have some message, or maybe an entire website, that you want to encrypt, you want to encode. And the first thing is we're going to turn that into binary just because that's how it's going to be represented. It's just ones and zeros. And of course, when we encrypt it, we'll end up with different secure ones and zeros. And we do this encryption by doing math, but of course, it has to be weird math. And what I mean by that is you might look at these like, okay, I get that these aren't numbers, but maybe we can represent them as binary, right? Where instead of the tens place and hundreds place, we have the twos place and the fours place, right? Surely that would work. But it doesn't, because in cryptography, the sets that we're working with have to be finite, usually. And sort of to explain what I mean by that, if you take two 3-digit binary numbers and add them, you get a 4-digit binary number. If you multiply them, you get a 6-digit binary number. These just get bigger and bigger and bigger, the maximum size you can have. And what we have here is operations that are, the 4 basic operations and a set of objects, in this case binary numbers, that they can act on. But this is not working out because that set is infinite, and we can't have infinite sets. Now you might say, well, okay, computers deal with unbounded numbers all the time. You can go and just into Excel and ask it, 43 plus 2, and you don't need to tell it how big the spaces are. But we can't do that for cryptography, because the trick is that those differently sized numbers, like maybe 42 and, some bigger number, it takes different amounts of time and they take different amounts of space, right? So if I want to do an operation for cryptography, it would take a different amount of time, and an attacker would be able to figure out, roughly how big the numbers involved are. So we can't use that because, an attacker deals by. We have to use fixed length, finite numbers. And the way that we are going to do that is with modular arithmetic, right? Which basically means we just keep going and wrap around. So you start, if you're counting like 3 plus 3, you're counting like 0, 1, 2, 3, 4, 5, 0, right? As soon as you hit 6, which is what we call the modulus, it just wraps back around. And of course, you can pick a different modulus and you'll usually get a different result. But it turns out that division, in this case, isn't actually well defined because it's possible to multiply things in a way that you can't actually undo it. So we can make division work and, be all happy if we enforce the constraint that the modulus has to be prime. Then division is well defined and everyone's happy. So there we go. We have the 4 basic operations, which we just do modulo, some prime number. And then we have a set of mathematical objects, numbers that we can use with them. In this case, it's just all the numbers up to stopping before p, right? Because at that point we roll back around to 0. And so when we take these two constructs together, right, operations and set, we call it a field, right? So the integers are a field. This sort of subset of the integers where we do everything modulo is a field. In this case, we call it a prime field. And a prime field is a type of Galois field. So we've gotten our first little hint of Galois fields, but we're not done quite yet. I will note, though, the way we write this. So if you see like GFP, that means it's a Galois field with p elements, right? what we've learned so far, this version can only have a prime number of elements. So P is some prime number. We can create GFP, but not anything else. And what's going to be useful for us is GF2, because that represents basically a single binary digit, right? A single bit, it can be either 0 or 1, and now we can do math on them, which is fun. So yeah, GF2 is going to be useful, but it's not useful yet, because obviously we have more than one bit. We don't want to do math with just a single bit. So, to make like a hierarchy, again, fields is this general idea where we have the 4 basic operations, add, subtract, multiply, divide, in a set that we can use them on. And you're probably familiar with the integers, which we write like this, but those are infinite. So we talk about Galois fields, which are basically just finite fields. Sometimes people even literally call them finite fields. And the prime fields are a type of Galois field, right? They're not the only one. We write them like GFP because they can hold, their Galois fields are finite fields with a prime number of elements. We don't want that. What we want are extension fields. And these can have a prime number to some power of elements. So instead of having just, like having 2 elements, which represents a single bit, we can have 2 to the 3 elements, which would like represent 3 bits. And we can imagine thinking about, how would we do this? Well, we'll start with just the normal definition of prime fields, right? Galois fields with P elements, GFP. And if our exponent is 1, right? If we only need to represent one of these things, then we'll just have it, right? GFP to the 1 should be the same as GFP. And so that's how we can define, GFP to the 1. But how do we store, more than one of these GFPs? Because we want to have, basically multiple copies. And the way we do that is with polynomials. So this might look a little confusing, but basically we're going to be treating polynomials like numbers. So we have a polynomial here. The coefficients, the A's, are elements of the prime field, right? So if we were using GF2, they would be 0 and 1, and we would do math with them according to, just do everything modulo 2. Right, so this is sort of the general definition, because we can make polynomials as big as we want. So this is how we have extension fields. We take normal prime fields, and we build polynomials where the coefficients are in prime fields. And now we can have as many, basically, individual elements from a prime field as we want, and so that's how we get these, like, prime number to some power. There is one problem with this, though, which is if I try to multiply 2 of them, let's say we're working in GF2 to the 3, right? Which means that our coefficients have to be less than 2, and our exponents have to be less than 3. These are 2 perfectly valid elements of GF2 to the 3, and if we try to multiply them, we get x to the 3, which is not, right? Now we have a similar problem, like when you have, go from you add 3-digit binary numbers, you get a 4-digit binary number. Now we have it, but it's with the exponents. So what do we do? Well, we can kind of do the same thing before, where we just do it modulo some polynomial, although the division problem comes in again. And so that polynomial that we're doing modulo over, the modulus, is a prime polynomial, which basically, if you think about it, like a prime number is just a number that can't be factored. It makes sense to say a polynomial that can't be factored. So that erases the division problem. We just have to use a polynomial that can't be factored, and then we do multiplication and also division modulo that prime polynomial. Although people usually call them irreducible polynomials because the name prime polynomial, that would just make too much sense. So yeah, there's that small note. But moving on, now we have the general definition of a Galois field, right? Which is just, it's a polynomial. The prime field is just a case when m is 1, so we only have a 0 at the end. But the general version of Galois field, we have a polynomial where the coefficients are in GFP, and addition and subtraction are just normal. We just use the normal prime field, addition and subtraction. But then, for multiplication and division, we have to do the modulo some irreducible or prime polynomial. And that's all there is to it. This is the actual definition of a Galois field. And the specific Galois field that we use is called the AES field. It's actually used for AES and GCM and all kinds of other stuff. It's super useful. It's kind of the default one. And when people say the AES field, what they mean is GF2 to the 128. So our coefficients, you can imagine a polynomial with 128 terms in it, and those coefficients can only be 0 or 1, right? So we're storing 128 0s and 1s. It's just like a sequence of 128 0s and 1s. And then we also need an irreducible polynomial to go with it. This can be any It just needs to be standardized, and this happens to be the one that is used for the AES field. And yeah, that's kind of all there is to it. So yeah, that's the secret behind AES is we use the AES field. So we do a bunch of math in the AES field to, compute the encrypted version of a message. But what about multiple blocks, right? Most messages are not exactly 128 bits in length. So we need some way to handle more than just a single block. And your first guess for how to do that might be to take your message and just, split it up into chunks. And then just encrypt all of those. This is a terrible idea because if chunks that are the same in PT is plain text, right? So chunks that are the same in our plain text, when we encrypt them and get a ciphertext, they'll look the same too. So anything that's the same in the plain text in what we're sending in will look the same once it's sent out. And this just makes it super obvious to see stuff. So you can see a video you might have heard of here that I've encrypted with ECB. And you can see that I couldn't look at the background and tell you what color the background originally was, but you can see what's the background and what's not. So yeah, that's a bad idea. So new plan, we'll introduce feedback. So we'll start with this guy over here, which is an initialization vector. So it's just some random vector that's public, everyone knows it, and it's just chosen randomly. And then we combine it with our plain text and encrypt that. And then the next time we have feedback. So the old ciphertext gets passed up to be combined with the new plain text. And so we get this sort of feedback pattern, which seems like it would work and actually kind of does work. It does work. It's used sometimes, but it's really, really slow, at least for, the standards that we expect for loading YouTube. So the reason it's slow, right, is that you can only run one of these at a time. You have to wait for the first, you have to wait to encrypt the first block before you can go do the second block, because it has that feedback, right? It depends on the ciphertext that comes out of the last one. So it's just really slow. But there's a new plan, which is totally different than block ciphers, except it's actually not that different. But this is stream ciphers, and stream ciphers encrypt each bit at a time. So they don't have the concept of a block, or if you want to think about it as the block size is 1 bit. But basically, you've got your sequence that you want to encrypt. And what you'll do is you'll use the key to generate a new sequence. So we'll generate a sequence, and what this sequence will do, it's called the key stream, because it's, derived from the key, and it's just this endless stream of bits. And that will tell us whether or not to flip each bit in the input, because we're working 1 bit at a time. All we could really either do is flip it or not. So we need to combine them where we say, flip the first one if the second one is true. This operation is called XOR, and it has a little symbol that looks like a plus with a circle in it. But that's basically all you do, is you generate a key stream, and then you XOR your input with that key stream, and it can be as long as you want. It's awesome. And so AES is a block cipher. But what we can do, what if we could do some magic to turn it into a stream cipher? And that's what GCM is. AES is a block cipher. GCM is a way of turning it into a stream cipher so that we don't have this block limitation. So we can encrypt messages of any size you could possibly imagine. So yeah, it's turning a block cipher into a stream cipher. All right, so let's talk about how it works. The way it does is we start with our initialization vector, and then we add 1 at the end, just like the number 1. If you see the 2 bars, it just means stick 2 things together. And then we encrypt that with AES, or, really it could be any block cipher, but we'll use AES, which of course requires our key. Then we'll go ahead and encrypt the initialization vector with 2 at the end, and, on and on with 3 at the end, as long as we need. And what we'll do is use the outputs from this as our key stream, right? So the plain text hasn't been involved at all yet. We aren't actually encrypting our message with the AES. We're using AES to encrypt a bunch of randomness and then a number that just keeps encrypting, and a bunch of randomness in 1 and a bunch of randomness in 2, right? So we're then using the output of that as our key stream, and we can XOR that with each bit of our plain text, and it's basically a stream cipher, right? We've turned it into a stream cipher. We've generated a key stream from our key, and we're using that we're just XORing that with our plain text. And so that gives us our delicious ciphertext, and we have completed encryption. There's just one problem, which is we haven't done authentication. Now, what is authentication, you might ask? Well, stream ciphers have a problem, and that problem is that if I go to ask for, let's say I go to ask for volleyball anime, and the service decides to send back some delicious volleyball anime. So it goes and sends it back. What it's doing, right, is it's taking a volleyball anime, and regardless if it's for any stream cipher, right, it's XORing it with a key stream. So we have, this is what's being sent back, is volleyball anime XOR key stream. And then, if I know, as like an attacker, there's two things I need. First of all, I need to know that you're watching volleyball anime, which, you know, I could find out other ways. And let's say that I can, you know, corrupt or like mess with your messages, so I can go in and change what's being sent. I can't see what's being sent, right? I don't know that you're like your secrets, but if I do know, like I know that you're loaded google.com or that you're watching volleyball anime, well then I can take that and XOR volleyball anime as bit. And remember, XOR is just like flipping, right? And so if you flip something twice, like you flip it and then flip it back, it does nothing, right? So these two XORs cancel out, and we have recovered the key stream. So now I could take soccer anime, XOR with the key stream, and then send that back to you. So everything looks good, it decrypts perfectly fine. But when you go to watch it, you get soccer anime instead of volleyball anime. And yeah, obviously there's more nefarious applications for this, but that's the idea, is if you can, like, encryption is, if I don't know what's happening, if I don't know what's being sent, can I, you know, read what's being sent? Authentication is, if I know what's being sent, or even if I don't know what's being sent, but if I do know what's being sent, can I somehow hijack the message to make it be something it shouldn't? So we need some authentication. It turns out we can do even better than just authenticating our, like, the actual message itself. We can tack on any additional stuff that we want to authenticate and make sure, you know, maybe this is going to be this additional data, right? It's going to be stuff that's public. We're not encrypting it, but we are authenticating it. So we're making sure that, you know, it hasn't been tampered with. So people call this authenticated encryption with additional data because it sounds fancy. But let's start with just XORing all this stuff. Lots and lots of XORs. So we'll take our additional data and all the bits of our ciphertext and we'll XOR it. And we're trying to get in the end some sort of tag. It's called a tag that can be used to, like, prove, you know, that it's authentic. So I should be able to look at the tag and say, has it been tampered with or not? And we'll also make sure that the lengths of everything, because we want to, you know, we don't want anyone, like, cutting off part of our message. That's a possible mode of attack. So we'll also add the links to this tag. But right now, we haven't really done anything with the key. We'll call it an almost tag, because there's nothing secure about it, right? If I want to generate, if I, like, can come up with a real tag whenever I want, again, all of this information is public and or known to an attacker who's, you know, seeing the message. So I can do that. I could also create a fake almost tag by just plugging in, you know, my fake ciphertext instead of the real one. So we're not quite there yet, but this is an important stepping stone. So you might say, well, let's just XOR it with something dependent on our key. That way we can make sure, you know, that it's everything's all in order. And, you know, an attacker won't be able to do this because they don't have our key. So let's say we'll do this. We'll start with, remember we started with 1, so it was like our initialization vector and then tag 1 at the end, or initialization tag 2 at the end. We skipped over 0. We'll use that now. So we'll take just the initialization vector with 0s at the end, encrypt that, and we'll XOR that with our tag. So we have this whole thing where it's just basically in the initialization vector encrypted. That's our key dependent thing that will mix into our tag so that no one else can forge it without knowing our key. Except this might look a little bit familiar, right? What we're sending back is our almost tag XORed with, like, this encrypted key dependent thing. Well, I can compute the real almost tag, XOR it, they cancel out, compute a fake almost tag, XOR it, and there we go. Now I have a fake tag. So plan foiled, day ruined, except there's really only one thing we need to do to fix it. The problem here is all this XORing, right? So what we can do is we need some way to, like, scramble it, depending on our key. We need to scramble everything before we XOR it. How do we do that? How do we do this scrambling? Galois fields! Yeah, so they're used in AES for a ton of things. They're also used in GCM, hence the name GCM is Galois counter mode. Right? So all we do is we treat them as elements of the AES field. We treat our, you know, each chunk is like each little bit that's going through. The way we scramble, you know, a collection of 128 bits is we treat that as an element of the AES field and multiply it by encrypting 0, which again, that's going to be key dependent. So we have this wonderful key dependent scrambling that you can't reverse the way you did with XOR. And yeah, this is it. This is the full original drawing of, like, the schematic of GCM. And that's all there is to it. Oh, and if you were wondering about whether we actually fixed that ECB thing, where, different things that are the same in the plain text become the same in the ciphertext, I GCM encrypted Bad Apple also.